Testing my microphone. Anybody hear me?
No, works well.
It does.
Oh, okay. Because I've been talking for about 3 minutes and and it wasn't working.
Now it's working.
Okay. So I'll start over. Christoph and Regina, I've made you co-hosts, if that's okay. And I've started the session recording. And our first presenter is Christoph Waldmann, who will lead a discussion on metrology. Christoph, can you share your screen?
I do my best. Okay. Here. Share screen. Is something going on now? Can you see something? All right.
Not yet.
Not yet.
Bildschirm file. Okay, sorry.
There you go.
Now it's. Can you see my screen now?
Yes.
Yes.
All right, so let's get started. Hello, everyone. I'm Christoph Waldmann. I'm working at the University of Bremen, Germany. I'm a physicist by education, and I've been involved in sensor developments and had interest also in metrology topics, because you immediately get in connection with those topics if you work in this business. Okay, so I will follow on the discussions that presentation that we had on Friday. And so my first slide is about why actually have a discussion on metrology, why it's so important and why it's relevant. And what you can see here is metrology offers concepts that are universally applicable, and they are very important to assess the performance of sensor systems and the measurements taken with those systems. So this is the first argument to say we have to look into that. We probably can learn from ocean science, from those methods that metrology is offering. And we also have to be aware that the data that are collected should be trustable. And so another argument to look into what metrology, what methods are available for metrology to raise the trust in ocean data. And as a third bullet points, I have here, metrology contributes to interoperability and enhanced reuse of collected data. These are the so-called FAIR principle that most people might have heard of. And this is something that I would wanted to raise. I don't want to go into details, but we can probably come back in the discussion part on why it actually contributes to this interoperability considerations. And finally, metrologists think deeply about measurements uncertainty. And that's something that is another argument why we should look into that domain in more detail. Okay, what we heard on Friday is a presentation by Shane Elliport, and Shane is also with us today, so he probably can make some comments on this and what I picked out from his presentation. He was showing us about the needs, why we have to be concerned about uncertainty quantification. And it's related to challenges from combined analysis of in situ and remote and model data. And so there's also a need to have an idea of quantification of uncertainty, which sometimes is also called error estimates. And that's something that we will probably come back in our discussion part. Okay, and the most fascinating comment that Shane brought up last Friday, for me at least, was a post that we were citing, and it was about how variability can masquerade as uncertainty, representation errors in satellite salinity. It's not just at satellite salinity, it's actually in all measurements that we are doing in ocean sciences. And saying this is really worthwhile to look into more detail, I guess. Maybe you don't find a solution to how to deal with it, but at least we can dig a little bit deeper and find out which direction we should go if we want to start a discussion on that. All right. Stefan Seitz, who is also with us today, he talked about metrological concept for ocean uncertainty quantification. And one of the most important thing to start with is to work on the clarification of terms like traceability, error, uncertainty, and so on. And so he gave a few examples about measuring error. And this is a very important thing. We should actually be a little bit careful in using error and uncertainties synonymously. This is not what we should do. It's the first lesson that you can learn from metrology, and this is actually also the base for the guide on uncertainty of measurements and also the international vocabulary on metrology. So people worked hard on thinking about using the right terms, and there was some confusion with this term error. And that's the reason why people want to get rid of it. But there's also the other aspect, because uncertainty is the quantification of the doubt that people have on the measured quantity. And here's some reason why this doubt can show up. And what I wanted to emphasize here is for the in situ community, it seems to be not very welcome to change these terms. So many people are still sticking to the terms that the international vocabulary on metrology would like to get rid of, like interchangeable use of uncertainty and error. But there are also other terms like accuracy, which actually are often used in a way which doesn't match the ideas of metrology. And this is another topic that people have to think about if they want to dig deeper into that topic. Okay, so what about metrology? How can it be part of the solution to quantify uncertainty? Actually, metrology offers a very nice concept. It offers method to decompose the measurement into individual components. This is a very nice idea, and this decomposition enables the individual assessment qualifications of the contribution to the quantification of the contribution to the overall measurement uncertainty. Okay, this is a very strict concept. It really helps to set up the so-called uncertainty budget, and from that you get the final number which describes the uncertainty of the collected value or of the observation. And so this decomposition is a little bit explained to a certain degree here with the terms that I listed below. It's part of that is the calibration, traceability, field stability, dynamic sensor response, and representation, uncertainty or variability. It's up to discussion how we should deal with that. So this is something that is still open. This has not been solved for ocean sciences, and that's something that maybe we can think about how to do the next steps. If you think about calibration, traceability, you probably can talk to companies like Seabird, and they will tell you they have ideas on quantifying uncertainty as part of the calibration process. So this is not something that we have to start from the beginning. And but still, I think there's a need to look into that. Not that every scientist, before he starts a measurement, has to go through all the papers and all the publications on that. But what we need to do is find experts. I think Stefan mentioned this also in his presentation. We have to find experts who compile all this information and define a method, a recipe, how to deal with that. So in the end, if you think about the scientist who is carrying out measurement somewhere in the field on the ocean, there must be a very simple scheme made available, which they can use they maybe look up the calibration uncertainties from the manufacturing companies. They think about these representation, uncertainty / error, and then in the end, they sum up this to the uncertainty quantification. We are still not there, but I think if we look into other disciplines, we can find some ideas on how they are dealing with this topic. And I'm particularly thinking of the World Metrological Organization, WMO. They actually came up with quantification of the measurement uncertainty. And you find that in reports. I looked into that a little bit and I found it a very good approach. It's very helpful to have that. But I must say, not sure whether they found the final solution to that. And definitely we cannot just transfer it one by one to the ocean domain. It's for their particular measurement systems and for their tools that they use. Just on the side, have you seen these weather measuring stations in the field, these white boxes, which you see sometimes? They are standardized. And so with these boxes, you can, loosely saying, there's uncertainty connected to that. If you build your weather station like that, position it according to the rules that they set up, you can assign uncertainty value for the temperature measurements there. That's the way how WMO is working with this, and I think that's okay, and that's a good example. So what I already mentioned here, this is the second bullet point. What we need to do is we set up task teams like WMO has done to develop these routines, this procedure for UQ quantification. And this is connected also with the standard operating procedures, SOPs, which means if you use a particular measurement setup defined by the standard operating procedures and look up the procedures that have been defined by the task teams, this is then the way how you come up with your uncertainty quantification. It's at least the way how WMO is dealing with it. Okay, and there's a final bullet point. Everyone knows we are dealing with existing procedure as part of the ocean best practice system. And we have Mark Bushnell with us. Mark Bushnell is leading Quartot. And Quartot has been instrumental in introducing QA/QC procedures for a real-time system. So they are there. And do we want to replace them? No, definitely not. What we will do is we will try to harmonize these procedures with our ideas. And that's what are the tasks that are ahead of us. Okay, and this is my final slide, questions or comments, and I'm looking forward to that. Thank you very much.
Well, thank you, Christoph. You can enter your questions in the chat box if you like, or just jump up and go ahead and ask a question. Christoph, I have a question.
Okay.
And it's maybe for you and Stefan and everyone. We use the term uncertainty quantification, but I usually want to follow that with the word estimate, because we can't be sure that we've identified every component of the budget, and we've made some assumptions in making that budget. So would you agree that the quantification is just an estimate in almost all cases?
Stefan, would you like to respond to that?
Yeah, I mean, indeed, if you take the GOM, it really talks about estimates rather than of quantification. So I think the word quantification is probably good in the context of oceanography, because it expresses that there must be a number, okay, in order to give a quality parameter rather than some kind of qualitative statement in terms of good methods and, well, as I've mentioned, some kind of flagging systems where it's very difficult at the end. You have a lot of flags, and okay, if all of them are risen and say, okay, then you can more or less say, okay, we have the best now, but what are you doing if you have one or two flags risen, and if you have even more quantities that you want to combine? How do you deal with this? And I think this is more or less impossible. So from this perspective, I would say quantification just says, okay, there must be a number at the end. That's qualifying a measurement result. But if you call this estimate at the end, or quantification, or number, or whatever, actually, I don't care. I think the most important thing is that it is a number and that you more or less follow the concepts that are behind uncertainty calculation.
Right. So I actually have a question to the audience. And so I was wondering about who is aware of any similar initiatives like the US CLIVAR? Has there been initiatives for certain parameters to quantify uncertainty? So if someone in the audience knows about that, would be good to hear from there.
Sorry. Christoph, I'm Rajesh Nair from the OGS, from Italy, from Trieste. And we've been working on this through JPI Oceans, for example. This is JPI Oceans calibration action,
right,
which has a few. You can find it on the website. It's still very primitive in the sense that it's just evolving now, because the problem with JPI Oceans is that you need the countries behind you. And so the problem is getting that political push. But we have the action active. And one of the things that we are trying to do through that action, we have a proposal that's that has been submitted to create a community. You know, it's those community building proposals. Bringing together the national meteorological institutions and the oceanographic institutes. And we hope to enlarge that. So, I mean, if the proposal passes, there's a possibility of working on this topic. Stefan knows about it because Stefan is involved. So,
okay.
So that's one of the things that could be interesting.
Okay, very good. Thank you.
I have a comment.
Yes.
And it's, I mean, just looking into the scope of these, what we're trying to achieve here is just a monumental task. You mentioned, for example, quartod, and just a little piece of quartod, for example, ADCP measurements, right? You address the uncertainty when the instrument is probably fixed. But what if it's measuring from a buoy, right? What are the motion properties of that buoy that needs to be included into the uncertainty of the measurement, right? You need to modify the sampling. You know, all those variables that are not accounted in the current standards and need to be somehow included there. And I guess this is a question is for the group. Is this group eventually going to evolve into some sort of a task group that addresses all those issues, or is this going to rely on an existing effort, which probably wouldn't be complete? So what is the way forward? I guess that's my question to the audience.
Okay. So, Raphael, thank you for the question. So my response to that is we should seriously consider whether this group that we have together here could form the core of such an activity that you were just describing. And I assume that for every parameter, maybe even for every instrument, for at least the EOVs, essential ocean variables, we have to figure out how to deal with quantification of uncertainty. So it's a huge task, but you cannot avoid it, you know, if you want to get serious on that. And so another remark that I want to make here is, if scientists say we want to stay away of that, so they don't need it for their investigation, for their process investigation, just okay. So we shouldn't force everyone to look into all the details. But if you do long-term measurements and derive any ideas for climate change effects or climate variability, I think you cannot avoid this. And therefore, I think there's a real need. And that's also what I understand from Shane Earlyport. And again, we should think about a way whether this is a core group or we should start a separate activity. But I would like to hear from other people what their ideas are, and maybe there are concepts that can be used or leveraged for what we have in mind. So, Shampika, can you hear us? Shampika? I see Shampika Kalaj, she's with us. All right.
Yes, Christoph, I can hear you. Yeah.
Thank you.
Hello.
I don't want to put you on the spot here, but I know that WMO has invested quite a bit of thought in that. Would you be willing to share your views on these concepts? Or
yeah, I'll try my best, because I'm not sure whether I have more than what you have mentioned to share, because WMO normally provides primarily for the surface-based measurements, as atmospheric measurements, the uncertainty quantifications in the manuals, primarily on WMO technical regulation number 8. And hearing to some of the comments here, what I think is that in some cases, for some of the EOVs and EOVs you are talking about here, can adapt what we have done to their, according to their requirements. But on top of that, the example that I heard a few minutes ago from someone telling about, when we are talking about the atmospheric, maybe for an example, atmospheric pressure measured from a buoy. So how you are going to take into account the buoyancy of the buoy and all that. So you in my mind, I think it needs to be addressed in two chunks, because the atmospheric measurement itself is one thing and the buoyancy is another thing. So you have some kind of quantification for the atmospheric measurement. On top of that, you have to think about that the additional element that comes into play for the complexities in ocean observation. So yeah, WMO has some examples that ocean community can take into account. And in some cases, there may be areas that you can even adapt some of these information that WMO has already established. Thanks.
Okay, thank you, Champika. I assume the WMO would also benefit if high quality data could be provided from the ocean science community, thinking about wave heights and so on. I think that could be of interest for WMO to get reliable data on that. Is that right?
Of course, because measurements like wave measurements are quite critical for WMO service delivery, especially the coastal inundations, those kind of forecasts. So definitely that will be helpful for the WMO community. And just adding to that, that I have mentioned in previous workshops also, that the WMO regulations, especially this measurement related regulations, does not contain many more information. I mean, information as much as we needed about ocean measurements in our regulations. So we need to improve that part to get the WMO members involved and to get their contribution to more towards the ocean community activities. So I think we have we have some work to do in introducing those information once this group or the OBPS community create those information, gather those information, we can include that information or reference to those information in WMO manuals, which will connect the ocean community standards and best practices into WMO community.
Thank you very much, Jean-Pierre.
Just an additional comment on that. This probably falls to the cracks in an audience like this, but from the engineering point of view, it is crucial to have a quantification of the parameters you use, because that eventually translates into safety factors, right? For designing anything from ports to coastal infrastructure. Well, I mean, design practically everything, right? But we take the ocean as a separate component, but from the engineering perspective, all those uncertainties needs to be quantified, including the human error factor that needs to be in the safety factors that are applied for design purposes. So this is very crucial. I have an engineering background, and I can tell you that safety factors are, as of today, they are quantified very, very, I don't know what word to use, but there's really nothing known about those, and a lot of assumptions need to be done. And an effort like this would certainly benefit significantly engineering practices.
I fully agree, Rafael.
I'd like to.
Yes, sorry. Yeah.
Oh, sorry. I would like to say that I do think this discussion is important, and I never really thought about the impact to engineering projects. And for someone who works for a Metrology Institute, I think if I would communicate at least to some of our managers that perspective, then they would be, I think, more on board to integrating their metrology with the field of oceanography. So I think that would be, could be a really important and impactful output from this group.
Yep.
That last comment, we got to move on.
Okay, just a short comment. Considering, okay, what could be the major task or outcome of this group? I think the most important thing at the beginning, before we think about any kind of technical details, how to quantify uncertainties and so on, is probably to come to a common understanding and a common decision that quantification of uncertainty is necessary. And because I have a little bit the feeling that you have a few persons, okay, who agree to this, but I think it's not a common sense in the complete community. And I think the first task of this group is probably more rather a political one than a technical one, okay, in order to promote the idea of uncertainty. Because if you do not have the uncertainty, you actually have no foundation for any meaningful decisions on measurement data. And this has to be carried into the community, into the best practices, into ocean databases. And I think how to do this should be one of the major tasks.
Yep, very good. Okay, let's
more comment very quick. I was gonna mention that maybe one way forward for this group could be to work on a white paper that synthesizes the recommendations that we are discussing during this workshop. So yes, people are interested.
I agree. Good idea.
Work on that.
Yeah, I think that's almost a given that we'll have something like that come out of this. Well, thank you very much, Christoph. It was a very good discussion. Let's move on now to Dr. Annie Wong. Dr. Wong is a research oceanographer at the University of Washington and the lead author of a paper titled, I had it here, the Argo Quality Control Manual for CTD and Trajectory Data that was just published this year. Annie, are you able to share your screen? And thank you very much for your time.
Oh, that's okay. Let me see if you can see my screen. Can you hear me at least?
Oh, yes.
Yes, we can.
Okay. Can you see anything?
No, not yet.
What about now?
No, not yet.
Let me click a few more things.
Okay.
Can you see anything?
No. If you like, I can pull up there. There you go. Perfect.
Oh, very cool. Okay, hi everybody. My name is Annie Wong, and I'm going to talk about Argo CTD data and their uncertainties. A very brief introduction. Argo is a global program that deploys profiling floats around the world's oceans. Every one of these floats carry a CTD that measures temperature, salinity versus pressure. There are floats out there that carry other sensors like biogeochemical sensors, but for today's presentation, I'm going to only talk about temperature, salinity, pressure, so data from the CTD and not from other sensors. The Argo program has been going on for about 20 years, and it's accrued over 2 million vertical profiles of temperature and salinity. The difficulties in evaluating data from profiling floats is that once a float is deployed, there are not many opportunities to retrieve them for recalibration. So how do we go about estimating float data uncertainties? I'm going to describe 3 methods that we've used. One is CTD checks prior to deployment. Second is long-term sensor monitoring in what we call delay mode analysis. Thirdly is global comparisons with independent shipboard data. There is a 4th method, which very simply is to retrieve the floats, bring them back to the lab for calibrations, but this happens so rarely that I'm not going to talk about it today. So let's go through these 3 methods one by one. First one is CTD checks prior to deployment. Some flow groups perform independent CTD accuracy checks to make sure that the sensor calibrations are within specification before deployment. These consist of checking the pressure readings against deadweight tester and checking the salinity readings against reference CTDs. CTDs that fail these checks are returned to the manufacturer for recalibration. We do this pre-deployment independent check because many things can happen to a CTD unit during shipping. Doing this pre-deployment check not only gives us some indication of the data quality at deployment, it is also a means to make sure that the CTD unit is operating properly before we deploy the float. Because obviously, after we've deployed the float, it would be too late to find out that the CTD is not working. Which brings us to the question of how do we monitor the float data quality over time after the float is deployed, because these floats can operate for many years without being able to retrieve them. We do this long-term sensor monitoring in what we call delay mode analysis. And in delay mode analysis, we look at a float time series versus a reference, and we see whether the float time series differ from the reference. So for pressure, floats usually take at least one quick P sample at the sea surface at the end of the telemetry period, just before they descend back to their park depth. This parameter is literally called surface pressure. For the parameter pressure, we look at the time series of these surface pressure readings, and here are some examples of these time series from many floats. If the pressure sensor is stable, these time series of surface pressure readings are mostly within ±1 of 0. But if the pressure sensor is drifting, these surface pressure readings will trend negative or positive through time, depending on whether the sensor is drifting negative or positive. In Argo, all the pressure are adjusted for sensor drift, and in all the Argo data files, we record the raw pressure values as well as the adjusted pressure values. And the adjustment is very simply the raw pressure value minus the surface pressure value. Here is a plot that gives you some indication of the amount of adjustment we've had to apply to pressure. At the edge of this plot is cycle number 280, which corresponds to about 7 years in a float's lifetime. And if we focus on the black line, which shows pressure adjustment greater than 2.5 decibar, towards the very end of the 280 cycle, which is around 7 years, only about 5% of the Argo profiles need pressure adjustment greater than 2.4 decibar. We pick, I'm focusing on this value 2.4 decibar because that is the pressure sensor accuracy that Argo use. In other words, most pressure sensors in Argo are fairly stable over the long term. Now, what about salinity? In salinity, for salinity, we do something similar, which is we look at a float time series of salinity and compare it to a reference. But unlike pressure, which we compare sea surface pressure reading relative to 0, in salinity, we look at salinity on a stable isotherm, and we compare it to reference data that are mapped to the float location on that isotherm. In Argo, we use 2 reference databases. We use CTD data from the World Ocean Database, and we also use Argo profiles that are judged to be good. And here's an example of what a salinity drift looks like. The blue line is the salinity values from a float on a stable isotherm. Stable meaning that salinity varies very little on that isotherm. The red line is the reference database mapped to the float location on that isotherm. And you can see here over time, the blue line trends away from the red line, which is the reference, towards the positive. This tells us that this float is drifting salty, basically. Okay, so similar to pressure, in all the Argo data files, we record the raw salinity values as well as the adjusted salinity values. The adjusted salinity is simply raw salinity minus delta S, and delta S is obtained from comparing to a reference database. Again, I want to show you a plot that gives an indication of how much salinity adjustment we need to apply to Argo floats. Again, at cycle 280, which is around 7 years, let's focus on the red line, which is the percentage of profiles that need salinity adjustment greater than 0.01. At around 7-year mark, about 40% of Argo profiles will need a salinity adjustment of greater than 0.01. And I'll tell you later on why we focus on this value 0.01, because I want to move on to the third method. The delay mode analysis that I just described is applied to each individual float one by one. And the correction is essentially an offset correction with no vertical variation. This third method that we use is a basin-wide analysis that analyze or evaluate the Argo dataset as a whole to check for any systematic bias, especially in the vertical. This global analysis is done by Susan Wiffels and her team at Woods Hole. I won't go into the details of this analysis because it's quite complex, but I will just really briefly describe it as Susan and her team, were able to come up with buddy pairs of Argo data and nearby GoShip data, nearby meanings nearby in space as well as in time. They look at the difference between the Argo, these buddy pairs of Argo profiles and nearby GoShip profiles on isopycnals. And this plot I'm showing you is sort of the final product that they've assimilated, after they've completed their analysis. This is the result for their pressure analysis. The first 4 panels show the 4 pressure sensors that we use in Argo: Payne, Emitek, Druck, and Kissler. Let's focus on the 5th panel, which combines the results from these 4 pressure sensors. It's a pretty complex plot, so let me really simplify this for you. Let's focus on the thick white line, which is the median of the difference between the buddy pairs Argo minus GoShip on isopycnal, but plotted in pressure space, so we could relate to it better. So think of the white line as the difference between Argo and GoShip. The 2 dotted black lines are plus or minus 2.4 decibars, which we regard as the pressure sensor accuracy. The conclusion here is that the white line varies between plus or minus 2.4 decibar throughout the water column. It doesn't show any systematic bias. There is no significant pressure bias throughout the water column, between Argo and GoShip. And any bias is within the sensor accuracy of 2.4 decibar. Similar analysis has been done for salinity. Again, the first 2 panels show the 2 seabird CTDs that are used mostly in Argo. They're the SBE41CP and the SBE41. The third panel combines the result from the first 2 panels. So let's look at this third panel, which is labeled all in the heading. Again, let me focus you on all the lines that are shown here. The thick white line are the differences between, the median of the differences between all the buddy pairs Argo minus GoShip. These 2 dotted lines are plus and minus 0.01 in salinity units. Conclusion here is the same. We don't see any significant bias in salinity between Argo and GoShip. And any bias we can see is smaller than plus or minus 0.01. Now, why do we pick this value 0.01 is because in several analyses we've done where we compare Argo salinity versus ghost ship salinity on a stable isotherm in areas of the ocean that are very stable, very uniform with very little variation. Invariably, in general, we find that Argo salinity differ from ghost ship salinity by about, in general, plus or minus 0.01 in salinity units. And so, because ghost ship salinity is very accurate, we consider it a good reference. And so we quote Argo salinity uncertainty at 0.01 in our data files. And so to wrap up all this analysis, the conclusion that we've been able to draw after doing analysis for many, many years is that after delay mode adjustments, Argo CTD data have an uncertainty of 0.002 degrees Celsius for temperature, which is the sensor accuracy, 2.4 decibel for pressure, which is again sensor accuracy, and 0.01 in salinity units for salinity. Now, these are general data uncertainties. In every Argo data file, we have variables called either pressure adjusted error, temperature adjusted error, or salinity adjusted error that record error specifically for that profile. In general, the numbers will be these numbers, but there are slight variations based on regions. Some of the more variable regions will have a higher error, or if we don't have sufficient information to evaluate long-term stability in delay mode, sometimes we quote a high error. So for users using Argo data, we always tell them, please, when you extract data from all the Argo data files, pay attention to the QC flags and the error bars that we quote in the Argo data files. All the material that I've presented today are in a paper that's just come out last week called Argo Data 1999 to 2019, 2 million temperature salinity profiles, subsurface velocity from a global array of profiling flows. It is published in Frontiers in Marine Science. It just came out last week. Here is the DOI, which appears on the screen if you want to read it. If anyone has any questions, please feel free to email me. Here's my email address on the upper corner here. And to finish off the presentation, I want to leave this slide up for discussion because we were asked to leave a slide up for discussion. Our colleagues want to mention that it would be good, and it's one thing that we could improve in future is for the scientists in the ocean community to collaborate more with manufacturers to tease out dynamic errors in the data, because all the data error that I've talked about are considered static data, but there are also dynamic errors in the data which are caused by instrument sampling in a dynamic environment. For CTDs, these are the CTD's motions through the ocean, which have spatial temperature and salinity gradients, and which lead to thermal lag error, CT alignment issues, etc., etc. So we thought that one way we could improve things in future would be for ocean data scientists to collaborate more with manufacturers, because they are the best people to tease out these dynamic errors. And I'll leave it at that.
Thank you very much, Annie. I enjoyed it a lot. It was pleasing to see the pressure errors leveling out over time and the salinity errors growing worse with time. Sort of something one might expect to see.
Yeah, it is a way to say that float salinity needs more taken care of than float pressure data.
Yeah. Are there any questions for Annie? I don't think I saw none in the chat.
Yeah.
I have a quick question.
Hello, yep.
Hi, Annie. Thank you very much for your very interesting talk. So maybe I'll have to look at the paper you just mentioned that just came
Yeah, I'll
out.
leave it up here for you.
Awesome. Is there anything being done about quantifying uncertainty on the Argo drift, like the drift velocity at 1,000 decibel?
Yes, there have been a lot of work being done. I do not have the details with me. I'd like to refer you to my paper.
Okay, great.
Yes, there. The paper is a systematic review. There are lots of references cited in the paper. See if you can find what you're looking for. If you can't find it, email me. I'll see if I can find them for you.
And then I just had a very quick comment, if I may. So I think in your last slide, you said that manufacturers were maybe the best people to talk to when trying to identify dynamical errors. I would tend to think the opposite, that oceanographers are the ones that are going to know better about identifying dynamical errors because of ocean dynamics. But just a comment.
Yeah, it's a collaborative endeavor, but what we find is that oceanographers tend to be able to come up with a better coefficient, and it would be good if these coefficients can be fed back to the manufacturers, and the manufacturers actually hardwire them into the onboard controller, the controller board on inside the CTD, so that this is so the alignment issues and the thermal lag issues are taken care of during the onboard processing, or at least oceanographers can tell the manufacturers what other information they need to be able to come up with better coefficients, like ascent rate is a very important piece of information for oceanographers who are interested in time response of sensors. But in the old days, the older style CTDs do not report ascent rate as such. So those are the informations that that are useful in a collaborative situation between the oceanographic community and the manufacturers.
Just a quick comment on that slide again, on the in regard with the manufacturer. This is from personal experience with a CTD on a glider, and it's not just dynamic errors; it's with the specifications themselves. So I had the experience that when we checked the glider sensors in the lab, it was very hard to meet the specifications of the manufacturer. So then I wrote to the manufacturer, and they told me that the specifications they cite in their sheets are for the CTD unit when it leaves their factory, and it doesn't have to match what happens when it's interfaced by the glider manufacturer. So you have an additional problem there, because a lot of the information on the data sheet is for the CTDs or the sensors themselves, but when you interface them to units from maybe another manufacturer, there isn't it isn't controlled a second time whether the specifications are the same. So, I mean, this is also a possible problem, I think.
Yeah, that exactly. Yeah, I think many people who've worked with autonomous instruments have that experience, that you cannot be too careful with the CTDs. There are many things can happen between a CTD unit leaving the manufacturer floor, to arriving at your lab, to arriving at the deployment location, to being put into all kinds of platforms, it always pays to be vigilant in every step.
Yeah. Thank you.
You're welcome.
Uh,
I would
can
also have, yeah, okay, go ahead.
Can I ask a question, Annie, in regard to your final slide, your dynamic errors that you were mentioning? So assume that these will affect the uncertainty of the measurements in different regions differently. Meaning if you are in strong gradients, you have a stronger issue with the dynamic error or dynamic lag correction than in other regions of the profile. Is this something that you also would consider to specify, say, okay, in certain regions you have different uncertainties than in others?
We find that the thermal lag error, as you say, is greater at the base of the mixed layer because that's where the gradient is highest. However, there's a, in Argo, there is an algorithm to adjust the thermal lag error. And after adjustment, that error bar is folded into the salinity drift error bar. So the error that we quote in all the Argo data files is the greater of the sum of those two errors or 0.01. Now it turns out that the sum of those two errors is usually smaller than 0.01. So in most Argo data files, you just see the value of 0.01 being quoted for salinity adjusted error. So the answer to your question is, yes, we do take that into account, but because the sum of those two errors, almost in all cases, is smaller than 0.01, we simply quote the larger of the two, which is 0.01. But at the background, we do consider it.
Okay, thank you.
Mark, you have to unmute your microphone.
Thank you. Annie, thank you very much again for your time and your presentation. Very enjoyable and a good discussion followed. I think Donata will introduce our next speaker.
Can you hear me? Okay.
Yes.
Okay, sorry, my connection is a bit spotty today. It's my great pleasure to introduce you Mikael Kuusela. He's an assistant professor of statistics and data science at Carnegie Mellon University. His work focuses on developing statistical methods for analyzing large and complex data sets in the physical sciences mostly, and he works in close collaboration with domain scientists. He specializes in questions related to spatio-temporal data, and this is what we will hear about today. Ill-posed inverse problems, uncertainty quantification, and statistical learning in large-scale physical science experiments. So I will leave it to Mikael to hear more about his work on mapping Argo data, quantities from Argo data.
Cool, thank you very much, Donata. So let me just see here if I can share my screen. Okay, so can you confirm that you can hear me okay and you can see my screen okay?
Yes, thanks.
Okay, very good. So yeah, thank you very much, Donata, for the invitation to give this talk and for the very nice introduction. So we will continue on the topic of uncertainty quantification for Argo data. And the previous speaker very nicely explained the things that go on at the level of the individual profiles and what is done to quantify the uncertainty at that level. And what I will do here is to talk about the next step, which is then to actually use those profile data for large-scale scientific analysis and how to quantify the uncertainty at that level. That regards basically quantifying the uncertainty of the gridded fields that are derived from the Argo data. And that has various challenges, as I will explain here. And as Jonathan mentioned, I'm actually a statistician, but I've been working with Argo data for several years now, so I have some familiarity with the data and some of the oceanographic questions, but my main expertise here is in statistics. Okay, so as we heard from the previous speaker, Argo is this global array of profiling floats that sample the upper 2,000 meters of the global ocean and measure temperature and salinity profiles. And we heard a lot about the individual floats and how they operate and what's done to calibrate them. And then when you go through that effort, you end up with things like this. So here is an illustration of all the Argo data for February 2012 at 300 meters depth. And I'm showing here the temperature data. So this is what the temperature data looks like when you put together everything from this array. And it's all nice and great. It has global coverage. You see interesting patterns here. But for scientific analysis, it's usually helpful to turn this into some kind of an interpolated field, like a continuous field that is then easier to analyze for scientific purposes. Now, in order to do that, you need to solve a spatio-temporal interpolation problem because, clearly you're not observing the ocean everywhere. There are gaps in the array. No matter how many floats you put in the ocean, you're not able to measure everywhere. So you need to find a way to fill in those gaps. So for example, in here where I'm pointing with my mouse, which hopefully you can see, we didn't have a float there, but you would ideally want to know what was your best estimate of the value of the temperature field at that location. So that's an example of a spatio-temporal interpolation problem, and there's a whole subfield of statistics that deals with problems like this. So the reason you can do this is that we know that the ocean is correlated across space and time. So presumably, we're able to come with a good estimate of the temperature at that location based on the nearby data one way or the other. And then the main task here is then to assign an uncertainty on that estimate. So as I mentioned, the big picture here is that most scientific analysis from Argo rely on these 3D data products. They take the irregularly sampled Argo data and turn them into these continuous fields. And there are many existing products like that. I have some reference there on the bottom. One of the popular ones, for example, is the Remick and Gilson climatology, but there are many others. But kind of a common thing with most of these products is that either they do not provide uncertain information or they use something that me as a statistician would see as fairly ad hoc techniques for uncertain quantification. So for example, the Remick and Gilson climatology, this is the last time I downloaded it, does not contain any uncertainty information. And the same goes for many of these other climatologies. Some of them do have some measures of uncertainty, but it's not immediately clear kind of what the properties of those are and are they exactly quantifying all aspects of uncertainty. And the reason these products sort of struggle to do this is that it's actually quite difficult to do. And the reason it's difficult to do is that the ocean is it's a very complex place, and these uncertainties, they depend on the spatio-temporal dependent structure of the ocean, which is a priori unknown to you. For example, they depend on these covariance length scales, which you also call decorrelation scales in your field. And these vary from one location to another in non-trivial ways. And the uncertainties very heavily depend on those kinds of parameters. So how do you get them if you don't know those parameters? And there are other complications as well. So for example, there's a lot of data, so anything you do needs to be computationally tractable. And the ocean actually turns out to be also a non-Gaussian place, so you ideally need some kind of non-Gaussian uncertainty quantification as well. Now, I've proposed one solution to address some of these issues at least, which is to approach this mapping problem using local interpolation techniques. And the idea there is that what you do is that you only work with local subsets of the data at once. You'd fit a model that is relevant for the local subset. And then you kind of do the interpolation problem in a moving window fashion where you move to the next grid point, you move the window, you re-estimate your model, and then you re-interpolate. And the reason this is helpful is that it's much easier to come up with these local models than to come up with some kind of a global model. but because of the moving window approach, you're still able to capture the global structure of the ocean. And furthermore, it's computationally tractable because you only work with these local subsets of data at once. So this kind of an approach has many benefits, among which one is better or more accurate uncertainty quantification. So that will be the focus here. You can look at our paper for some of the other benefits of this, but here the focus will be on the uncertainty quantification aspect. So in some more detail how this works, so let's say that you want to get the interpolated value of the field at this location here. What we do is that we look at a local spatio-temporal neighborhood of that data point, or sorry, that grid point, and then we look at data in that neighborhood. And what we do is that we assume that within that local neighborhood, the process is a stationary Gaussian process, which is almost the same as saying that you do what you call objective mapping or optimal interpolation. It's those Gaussian processes and those techniques kind of go hand in hand. But one of the differences between existing things and what we do is that we estimate the covariance parameters of the process from the data. And this is something which is actually fairly standard in statistics, but before our work, this was not standard in oceanography, but it can be done and it should be done. And I will show you in a second that it actually produces fairly reasonable estimates. And then we do that. We then use the estimate length scales and use them to interpolate and also to get the relevant uncertainties. Once you know the length scales, then more or less everything after that follows quite easily. And then so that's to get the estimate at this point. When we then move to the next grid point, we move the window. There's some new data that enters. There's some data that is left out. We refit the model. So we now get a new set of length scales that is maybe slightly different because you're in a slightly different region. Then you can interpolate. You get the point prediction and the uncertainty at the location. And then you continue like this until you have covered the global ocean. I also briefly mentioned that we try to account for the non-Gaussianity of the ocean, and the way we do it is that we have in our model we have a heavy-tailed fine scale variation, which in this area is called the nugget effect, and that allows us to partially handle heavy tails in the Argo data. So we go through this procedure, and then we get interpolated fields like this. So this is the temperature anomaly for February 2012. And this is from our data-driven procedure. So we have these data-driven length scales. And as you can actually see from this map here, the length scales are longer near the equatorial regions. They become shorter towards the poles. There's anisotropy in terms of the things are kind of stretched in the zonal direction and so forth. And all of these are features that I believe your community kind of expects the ocean to have. We can look at the length scales. So here's one plot of what the length scales look like. So here I'm plotting the sort of the zonal correlation at a fixed spatial distance. And what you see here is that the ocean or these length scales behave the way you would expect. So they are longer near the surface and become shorter as you go deeper. And also in terms of the latitude, you have patterns that seem to make sense in terms of the physics of the ocean. These are all from the data. So this is extracted from Argo data. This was not an assumption we built into the model, but we're able to get these kind of patterns that at least people like Jonathan and others tell me that make a lot of sense. So now we have this, and this procedure has various benefits. One of them is improved uncertainty quantification. So let me focus on that here. So this is one way of visualizing the uncertainties. So on the top row is a visualization of our uncertainties, and on the bottom row is a visualization of the uncertainties from my re-implementation of the Remigan-Gilson climatology. So these are uncertainties for Gaussian processes. But I should actually first explain what's in the figure. So I'm plotting here the ratio of the post-data variance to the pre-data variance, which means that first of all, the color scale here goes from 0 to 1. So if it's blue, the ratio is 1, meaning that by observing Argo data, you were not able to reduce your uncertainty of the temperature at that location. And if it's a reddish color, then it's close to 0, meaning that by observing Argo data, you were able to almost certainly know what the value of the temperature was at that location. For Gaussian processes, which these are, the uncertainties depend only on the locations of your observations and on the length scales. They do not actually depend on the value of the actual observation. Because we have these data-driven length scales that look different at different depths and different locations, we're also able to get uncertainties that look different at different depths and different locations, which is in stark contrast with basically what the Römig and Gilson approach would give you, because they actually have the same length scales at every depth. They do have some spatial variation in the length scales, but they have the same length scales for all depths. And as a result, you get the same uncertainties at all depths, which doesn't seem like the most reasonable result at the end of the day. So here's this is a fairly big qualitative difference between the uncertainties we get and some of the previous uncertainties. And we can go ahead and validate this. Here's a table with a lot of numbers. I won't go through all of it here. I'm just telling you that you can actually check whether your 95% predictive intervals actually contain the true value 95% of the time or not. At that particle level, our method is doing a pretty good job. Let me show you actually maybe a better visualization of this here on the next slide. So it's effectively doing that same check, but at every possible level. So not only 95% to 68%, just kind of looking at the whole range of the distribution. So basically what I'm plotting here, I'm plotting after a certain standardization, I'm plotting the theoretical quantile of the predicted distribution versus the difference of the sample quantile and the theoretical quantile. And that might be a little bit difficult to get your head around what this exactly means, but let me just tell you how to read this plot. So the way you read this plot is that there would be perfect calibration if you had a flat line at 0. So if you had a horizontal line at 0, then these predicted distributions would be well calibrated. And what is clear here is that it's not a flat line at 0. So all of these have issues with calibration to various degrees. In particular, the existing model is quite badly calibrated, and that's because of the length scales which are not necessarily always completely appropriate, and then the fact that it's a fully Gaussian approach. Or well, I should be maybe a bit more careful. That product does not report uncertainties, but if it did, they would probably report this kind of Gaussian uncertainties. So that's what I'm kind of assuming here. And if you do that, it's not particularly well calibrated. Then the orange and yellow lines are fully Gaussian uncertainties. They're better calibrated, but still not perfect. They have this kind of an S shape, which is indicative of heavy tails. So that's why we put the heavy-tailed nugget effect to the model, and that gives us again an improvement in the calibration. It's still not perfect, so there's something more here that should be done, but it's showing at least an improvement. The key point here is that if you want to get realistic uncertainties from these products, you need to have realistic length scales, which you can get from the data, and you need to account for the non-Gaussianity of the data. Okay, so let me go on and then talk a bit more about how you then use these products. So at this point, we have discussed about how you produce the product and how you get a certain type of uncertainty quantification for the product. But then what you want to actually do at the end of the day is to do science with these products. And very often doing that involves looking at things like integrals over a region. So here's an example for the ocean heat content, or some other combined metrics of the maps. So indeed, let's focus on the ocean heat content as an example. So the ocean heat content is a three-dimensional integral over the global ocean of temperature effectively. And one dimension of this integral you get for free by just integrating the vertical profiles. So now you're left with this spatial interpolation problem for these vertical integrated profiles in order to get this ocean heat content. Well, we can do that using what I just described. So we can use these locally stationary Gaussian processes to solve that interpolation problem, and then we can just integrate over that map field, and we get a value for the ocean heat content, and we can do that various times, so we then get a time series. But if you want to get an uncertainty on that, there's a bit of a problem here, because if you want to get an uncertainty on something like an integral, you actually need the covariance between different locations in space. And from this previous approach, we can quite easily get point-wise uncertainties, but given the local approach we have taken, it's a bit non-trivial to get correlations across different locations. Like the trivial approach for that would involve having some kind of a global covariance model, which for various reasons is not really tractable here. So, however, we have recently come up with a way of doing this, and it goes by the way of actually not explicitly constructing a covariance matrix. It goes by a way of producing conditional simulation ensembles from these maps. What that means is that so underlying these maps, so if you look at something like this, there is a distribution. This is the mean of that distribution, but there is a high dimensional distribution that captures our uncertainty of this map. So we have a way of sampling from that distribution, and those samples, we call them conditional simulations. Those represent our uncertainty of the field, including its correlation structure. So let me show you how this works. So here's again, this is a mapped field. This is the mean of that predictive distribution, that high dimensional distribution for this map. Here's one conditional simulation realization from that. So again, this is a realization from that high dimensional distribution for which this is the mean. At any given location, sampling this would give you the variance at that location. But the point is that when we sample a map, we also get the correlations across different locations. And this is done in such a way that it captures the predictive correlations we have given the data we have and the model we have. So, okay, so here's one realization, here's another one, here's a third one, and then we can keep doing this. And then what we can do is that we then integrate these simulations to get quantities of interest like the ocean heat content. And because each simulation is different, we get a spread of those values, and that spread is a reasonable measure of uncertainty for that underlying quantity. So we can put that together, and then we get something like this. So here's, you see the time series of the ocean heat content. This is the ocean heat content anomaly, so we have removed the trend and the seasonal cycle. So you get the time series, which is kind of easy to get from the previous approaches. Then we also get these uncertainties around the time series, and that comes from those conditional simulation ensembles. And you can see that this is immediately used for scientific purposes. So for example, based on these uncertainties, you can say that around 2015, when there was a strong El Nino, we can now say that the ocean was statistically significantly, it had a statistically significantly higher amount of heat than at the normal year. So you know, these kind of uncertainties are immediately scientifically relevant and useful. Okay, so let me just wrap up here. The high-level conclusions here are that the Argo community has a very sophisticated approach for data management and quality control, and the previous speaker did a really good job at explaining those aspects of the Argo project. But what I think is much less developed is what happens after that, which is the mapping part. And I think actually the next speaker will talk about the other approach, the data assimilation approach, which I think has a lot of related issues and questions. So those things also require uncertainty quantification. That's very challenging. It's in this case, it's challenging because of the complex spatio-temporal dependent structure in the ocean. And we have certain ways of doing that, but there are certainly things we can do better. And then the fact that the ocean is actually seems to be a non-Gaussian place, and a lot of previous approaches rely on Gaussianity, you know, based on Gaussian processes, and going beyond that is actually quite difficult. And as a result of those complications, many of the existing products actually do not have uncertainties, or they use relatively ad hoc techniques for uncertainties. And the issue is that if you do not provide that uncertainty information in the products, there's no way you can get rigorous uncertainties for things like ocean heat content and other derived quantities from Argo, So for example, getting a spread like this is simply not possible with the existing products because they do not include that information. And that's a concern, because if you want to do science with these things, you ideally would need those uncertainties. A further complication is that it's not enough to have pointwise uncertainties, because for many quantities you actually care about, they involve several locations. So they involve things like integrals, derivatives, or some kind of aggregate information across several locations. And to get an answer on a thing like that, you would need access to the predictive covariance information. And I think a good way of having that access would be to produce these conditional simulation ensembles. So that's something I have been advocating for a while now, and I think I will keep advocating, which is to try to have in data products these kind of conditional simulation ensembles, which is actually very similar to what is done with climate models already. They also have this kind of ensembles to quantify the uncertainty or the variability of those models. So this is sort of very analogous to that, except that now we're talking about ensembles for the predictive distribution that is underlying the data product. So I'm kind of hopeful that the community would pick up on this, because I think it just fits very nicely in what is needed here. So yeah, so we were asked to put up some recommendations. So here's my last recommendation slide. It more or less contains the same information as in the previous slide, but maybe if I just very quickly go through it, and then we can have a few minutes for discussion. So, okay, recommendation 1 is that data products should have uncertainties in them. It's not enough to have pointwise uncertainties. You should also have some covariance information like these conditional simulation ensembles. Another very important point is that the decorrelation scales and other covariance parameters can be estimated from data, and I think they should be estimated from the data, and we have a method for doing that. It would be ideal to try to go beyond Gaussian uncertainties. It's actually difficult, but it's not completely impossible, and at least to acknowledge that the ocean is non-Gaussian, meaning that Gaussian uncertainty quantification by itself might not be enough. And finally, I'd like to say that these are actually very non-trivial issues, and you don't have off-the-shelf solutions for these things. So maybe the most important take-home from this is that I think there needs to be more interaction between the oceanographic and the statistics communities, because this is really the kind of place where statisticians can contribute, and hopefully, you know, we can have this kind of fruitful interaction where both communities can benefit from the challenges and expertise that we have. And yeah, with that, I think that's all I want to say. So I'm happy to take any questions you might have. Thank you.
Yes, I have indeed a question. Even though it's actually not addressing you directly, but more all the people who are listening, because I'm a little bit confused if I compare your talk to the talk that I've heard before. Because after listening to the talk before, I had the feeling, okay, there is some kind of uncertainty. Maybe not exactly as metrologists would calculate it, but at least there is some data or some number assigned to the as an uncertainty to the Argo data. But now I listen to your talk and you say exactly what's written there. There is no uncertainty information coming with the Argo products. Now, how does this fit together? I mean, on the one hand, there is data available, obviously, but if you want to use the data, you do not get uncertainties.
Yeah, okay, so let me clarify that because I know what the answer and what the confusion is. So, okay, so here I was talking about the credit data product. So, okay, so Argo produces at least 2 types of data sets. So there's the raw profiles and collections of raw profiles, and those have uncertainties, as the previous speaker has discussed. So when you download a database with raw profiles, that data file contains the uncertainty of those profiles. But then there's a separate effort where groups of researchers take those raw profiles and turn them into maps like you know, let's say like this one here. So that step usually doesn't have uncertainty quantification associated with it, or at least not communicated in the products. So if you go ahead and download these existing credit data products, they often don't have uncertainties. So it depends what level we are talking about. At the level of individual profiles, there exist uncertainties, as the previous speaker has discussed. At the level of these maps, very few of those products contain uncertainties.
One other clarification, just to make this clear, like the mission of the Argo program is to collect this data globally and provide the profile data to the community. Then the community takes those data and does analysis, grades the data, shares the results. So it's two different things. Like the mission of the Argo program is really to collect this data, provide profile data to the community, and that's what Annie was describing. Then what individual groups do with the data is a different story. And that's like, one of those efforts is what, we're working on with Mikael to produce gridded products from the Argo data that the Argo program provides. So just to clarify that. And I want to thank Mikael for this talk. And I was wondering, like, if you could briefly comment on the other challenge that is part of this story. Here you talked mostly like about the mapping of the anomalies. And then there is the challenge of putting uncertainties on the mean field that you need to get to the stage of mapping the anomaly. So I was wondering if you would like to share any thoughts on that with the group.
Yeah, well, that's a very good question. So yeah, I talked here about the anomalies, but yeah, so what goes into the Argo mapping, there are two things. There's the mean field, and then there are the anomalies around the mean field. So maybe in different terminology, there's the climatology, and then there are the anomalies. And the answer of the climatology is a whole separate question, and it's actually quite difficult because there we're not only talking about the kind of the data, kind of the variability from the data, but there's also a major issue with modeling. So I've actually found out that actually modeling the mean field is surprisingly difficult. So we, for example, with Donata, we've been working on time trends of ocean heat content, and we found that those time trends are surprisingly sensitive to the way you do the modeling. So now we're actually not only talking about sort of statistical uncertainties, we're also talking about systematic uncertainties. So in many areas of science, people differentiate between at least two types of uncertainties. There are the sort of the aleatoric uncertainties, and then there are the epistemic uncertainties. The first one is related to kind of random errors, and the second one to systematic errors. And for the mean field, there is a major issue with those systematic uncertainties, which relate to the way you model the mean field. And quantifying such uncertainties is actually even more difficult. It's not completely impossible. There are things we can do, but yeah, it's a separate issue, and there's sort of a separate set of challenges related to that.
I have a question. I'm assuming that when you define the time lags and the space to do the correlations, or not the correlations, but to do your analysis, there's some variations in the final estimation of uncertainties. Is there an optimum time step or not step? I'm struggling now with all these concepts of trying to unify the language that you need a period of time for these, and also a spatial area, right? Is there an optimum that you need to get to, or I mean, is it defined somewhere? Could you just comment on that?
Right. So if I understand your question correctly, you're asking that when we use these local windows, the estimates presumably depend on what window size we use. Is that
exactly?
Is that the
Yes.
right understanding? Yeah. So so that's correct. We have done some analysis of that, but there's a lot more that we probably could and should do on that topic. Ideally you would want to use as small windows as possible, because the underlying assumption here is that the process is stationary within the window, and that assumption is better satisfied for small windows than for large windows. But then there's the kind of the flip side, which is that if you make the window very small, then you don't have enough data to constrain these things. So that's what we call a bias variance trade-off in statistics. And one could probably come up with some way of optimally picking that kind of a point in that trade-off. we haven't looked at that super carefully. One thing we have found that, again, as Jonathan mentioned about these mean fields, we found that the mean fields actually tend to be surprisingly sensitive to the size of these windows. I didn't talk about here how you estimate the mean fields, but there's also this kind of a local window approach for the mean fields. And that was more sensitive to these windows than I expected. For the anomalies, it doesn't seem to be super sensitive to the window size. So for that, it doesn't seem to matter so much as long as you're roughly in the right ballpark. But what I found is that surprisingly the mean fields are quite sensitive to the choice of the window size, and clearly more studies should be done to try to understand how to pick that in an optimal way.
Yeah, thank you. And just another comment for the group is, I think that something that we need to document somewhere is that every level of processing of any product should have an associated estimate of or a quantification of uncertainty. That's something that is lacking, and we need to stress that that's required.
And also, like, so all of this is like a pipeline, right? And it's actually important that, like, at the first levels of the pipeline, you have uncertainties, because if you don't have uncertainties at that level, then there's no hope of getting uncertainties at the further levels. So that's why it's so important what Annie, for example, was talking about, that we have uncertainties at that level of the individual profiles, because if we did not have that, then, you know, all hope is lost after that. So the further you're kind of, you know, depending on where you're in the pipeline, it's you know, especially important that you get uncertainties, especially if you're kind of on the first stage of the pipeline.
Yeah.
All right, very good, Mikael. One more comment, and then we should move on.
I have a question, Mikael. Does your method just quantify the uncertainty of the interpolation method, or does it also consider the observational measurement uncertainty that Anna was talking about before?
Yeah, that's actually a very good question. So, well, I can skip. I have in the backup some more technical details of this, so let's just go here. So the model we are fitting is one like here, and this epsilon ij term would be the one that would contain that measurement error. Now, we did everything here for temperature fields, and as Annie mentioned, the temperature sensors are very accurate, so we actually don't worry too much about that, so we didn't particularly pay special attention to that. If we did this for salinity or for some other quantities, then one would need to worry much more about that, because the salinity sensor is less accurate. So if you did this for salinity, you would explicitly add here sort of an epsilon term to quantify the uncertainty of the salinity sensor, and that can be done. That's actually quite, I mean, that's actually very, very well understood in this area of statistics. Assuming that you have access to that information in the data files, and as a result of Annie's work and the work of others, we have that information. So you can do that. You can build it into the model. We didn't explicitly have it here because we're not too worried about the uncertainty of the temperature sensor, but for salinity sensors, one would ideally want to add that term to the model.
Okay. Thank you again, Mikael. Very, very much appreciated.
Thank you.
And Donato will introduce our next speaker. Will I? There you go. Thank you.
Very happy to introduce Patrick Heimbach. Patrick is a computational oceanographer at the University of Texas, Austin. And his research focuses on ocean and ice, so sea land dynamics and their role in the global climate system. Patrick is an expert in inverse methods for bringing together ocean circulation models with available satellite and in situ observations. And the goal is to really produce the best ocean state estimate. And in particular, the ECHO state estimate, which is a dynamically consistent estimate of the ocean. One aspect of this process is uncertainty quantification in the context of data simulation. And today we will hear more about this from Patrick. Thanks, Patrick, for joining us.
Thank you very much, and thank you for giving me the opportunity to speak in this interesting session. So yeah, uncertainty quantification in the context of data assimilation. In order to talk about this, it's good to remind ourselves what data assimilation is about, why we do this, and I always like to start to pointing out that the perhaps a little bit unpopular notion that I consider oceanography to some extent as a sparse data science, and I think that's part of why we are discussing some of the issues that we are discussing. This shows an example from a review paper by Abraham et al. 2013 about the sort of taking stock of all the in situ observations of temperatures that we have, where you see in this figure, here, the top Northern Hemisphere distribution of the number of global coverage as a function of time in years and depth. The same for the Southern Hemisphere. You see this very sparse sampling prior to the 2000s, of course, and with the 2000s picking up with the onset of Argo data profiling. But even this still shows us the, just the top 2,000 meter depth. And then the right figure shows you the distribution as a function of latitude, where you see this is skewed towards the Northern Hemisphere in terms of the percent of the sampling as a function of latitude, but that contrasts with this green bar, the global ocean volume, which is more sort of sits more in the Southern Hemisphere. So we have there are many places that even today remain undersampled, and so we. Let's see, let's keep having, okay. So what's data assimilation? I like to use this nice sort of sentence. It capsulates a lot of the aspects by paper by Kaminsky et al. 2015. Major goal of it is that ideally all observational data streams are interpreted simultaneously with the processes information provided by the equations of motion. So this is where the model comes in, which then leads to a consistent picture of the state of the system that balances all the observational constraints and taking account of their respective uncertainty ranges. So the provision of uncertainties for each of these observations is an integral part of data assimilation system. An example of this, Nata nicely highlighted this, is the ECHO, which is a multi-platform, multi-instrument synthesis. Reconstructions over the last 2 to 3 decades of the global ocean circulation, incorporating satellite and in situ data. I'm not going to talk too much into this, but you see sort of all the different data streams that go into this product. And so, as we've said, so data assimilation, what is uncertainty quantification in the context of data assimilation? I think it's important to also recognize ECHO is, of course, one application of data assimilation. It's what we would call reconstructions or state estimation, but there are other uses and applications of what's sort of more widely considered as an inverse method, right? And so some form of data assimilation do this for parameter estimation or calibration. So for these applications, the goal of uncertainty quantification is that we seek the uncertainties in the parameters that we're inverting for, or that we're trying to optimally estimate. In the context of state estimation or reconstruction, or which is a form of interpolation, which is what ECHO and other reanalysis projects are doing, our goal is ultimately to seek uncertainties in the reconstructed state, so the global ocean state, temperature, salinity, sea surface height, and so on, or in derived quantities or interest or metrics, right? You could think of, that these reanalysis products, we can derive all kinds of diagnostics, AMOC strength at a certain latitude, or Drake passage transport, heat content, and so on. And so these, we can propagate the uncertainties from the full state into these derived quantities. Or, of course, importantly, and that's, I would say, probably still thought of as the major application, especially in meteorology, data assimilation is for forecasting purposes, right? So it's a problem of extrapolation. So in that sense, we then seek the uncertainties in the forecast. So these different applications, important to keep that in mind. Data assimilation can do many different things, and sometimes also the methods that are deployed will vary somewhat according to the applications of when we use data assimilation. So the origins of uncertainty, so where do uncertainties arise and come in the context of data assimilation? There's a number of sources. One is the observations, and a lot of it we're discussing today. Observational error is the measurement error, and as we've nicely seen, sort of the issues of drift and so on in these data, and how and trying to quantify and get. But there is a second one, which is the one of sampling in space and sampling in time, and how we deal with this. If we have a point-wise measurement, and will become very important in the context of a model that has a much larger footprint, right? So global scale models, sometimes with footprints of, let's say, the order of 50 by 50 kilometers, that have a lot of variability within that, or temporal aliasing as one issue. The second one is the assimilation scheme itself, right? So the approximations that we have to perform for a data assimilation algorithm to be computationally tractable, for example, right? Or how, even for within the same system, by what way do we ingest observations into the data assimilation system? Are we using gridded Argo data as a form of assimilation? Are we using them pointwise when they arise? Are we using satellite data as a long track satellite data or as gridded product? All of these will have an impact on how the system will digest, and also an impact on what kind of uncertainty bars we then assign to these data. The model, of course, very important. The model that serves as the interpolator, the one form is parametric uncertainties. Think about, mixing coefficients that are parameters that we can, but also structural uncertainties. So the discretization, model inadequacy. So this would be way of structural uncertainties. Have we provided the right formulation for, the boundary layer mixing, or any other form? Then all the boundary conditions, all the inputs that we have to provide, the external forcing, right? In the forced ocean simulations, we would have to provide the atmospheric state, or sea fluxes, they come with uncertainties. The bathymetry has its uncertainties. Natural boundary conditions have these uncertainties. And then prior knowledge, the use of prior knowledge in what we sometimes call background error covariances. So these come in as priors. And so dealing with all of this is extremely difficult. And so here are some reasons why typically I would argue, especially in reanalysis and reconstruction, we haven't seen convincing approaches so far in terms of really trying to quantify and assessing the uncertainties. And part of the reasons is, well, they're very difficult to account for the inhomogeneous sampling. And especially when we go back in time, over the last 20 years, the last 50 or 100 years, the increasing sparsity of the data. The parametric uncertainty is sometimes called the curse of dimensionality. If you allow a mixing parameter to be uncertain in 3D space, you're quickly dealing with a 10 to the 6 dimensional uncertainty parameter space. And the structural uncertainty, how do we capture those? How do we capture that a given form of parameterization scheme has not been well defined? And so these are some very, very serious and very complex issues that are computational in nature, that are actually even fundamental science in nature, right? So how do we resolve them are sometimes very hard science questions at the core. And just to point out in a very simplified and crude way, sort of like to point out some conventional approaches of how we deal with it today. For parametric uncertainties, for example, it's often deals with ad hoc tuning of ocean and climate models, where in the inability to rigorously tune 3D fields of mixing parameters, we have parameters that they are single or values, or where very experienced model developers will know how to tune these parameters by comparing them to models, but really more based on experience than based on formal, let's say, mathematical algorithms, or the uncertainty being defined mainly as a spread of an ensemble of simulations, like take the ensemble of different reanalysis products to look at, how much we trust sort of heat content changes. This is, one can clearly, it's a measure of uncertainty or an estimate, but there's a number of shortcomings with this. And for example, we we cannot, for example, looking at these ensemble, we cannot account or rigorously trace back to sources of these uncertainties. How do they come in? We can sometimes, it's hard to understand what are the causes of the ensemble spread, right? For example, for reanalysis products that are where everything is different, right? The model is different, the forcing is different, the data assimilation scheme, and so it's, you know, with everything being different, they almost have to be different schemes. And the question is, what's the cause? What's the major cause? And so these are shortcomings, and again, these are difficult things to deal with. And so inverse methods again offer tools for rigorous, well, trying to be formal methods to perform uncertainty quantification, but they also have their drawbacks, many of them being just computationally much more complex than even the data assimilation and the forward modeling itself. And so there's two main sort of categories I'd like to sort of distinguish between. The one is sort of more the sampling approach, Markov chain Monte Carlo methods, where you're trying to really sample from the uncertainty space. This is very appealing, and it also allows you to deal with a number of, for example, non-Gaussian distributions and so on. It also comes with this very complicated, well, the very serious issue that, you know, sampling, you have to find sort of low dimensional parameter spaces so that you can actually do these type of sampling exercises. Compared to that, we have what we call derivative-based parameter state estimation framework, where we can use the virtue of the adjoint, basically, that allows us to compute the sensitivity of your outputs to, especially if that output is single valued, like quantities of interest, to the inputs in a very computationally very efficient way. And so this is this is sort of what I'd like to highlight in the following, just to show you again, sort of that the good thing and the bad thing of data assimilation is that we have these three main ingredients. We have the observations, the error, the model, and then the error in this least square cost function. And we have to, you know, in order to do data assimilation, we have to think about all of them, because we have to plug in some number, right? So you cannot run the assimilation scheme without having plugged in an error estimate. And so the good thing about this is you have to actually think about, what is it that you plug in? Are you plugging in for the sigma squared? Is this your formal observation error, or has this to be the representation error that represents the unresolved scales that you have, that mismatch between the model and the observation? I'm just trying to highlight, to point this out, that, you know, the data assimilation at least forces you to put a number in, right? And it then forces you to improve this over time, and that makes it an iterative process. The uncertainty propagation within this data assimilation becomes sort of a geometric aspect, and you can think of here, when we have this misfit function that we're trying to optimize. The first derivative, of course, gives you the gradient. It tells us how do we change our inputs in order to achieve or come to the minimum. But then when we are at the minimum, we can see, if we see here, two sort of directions. The one is here in the green, the other one is the blue. You can see that this parabola, or this multi-dimensional parabola, is well constrained in one direction, means the curvature is very high, right? So a small change in the input leads to a very large increase in cost, and therefore you have so that gives us this curvature gives us a measure of the uncertainty. In the other direction, the curvature is very weak, which basically means this misfit function is very poorly constrained, right? And so this is basically a geometric interpretation of what I said is the derivative information. And in rigorous, so UQ, we call this the Hessian, or that's the second derivative. So we're really trying to find the curvature of our misfit function with respect to the inputs. And we're looking at, we can now do a multidimensional decomposition and actually find the regions. What are the dominant regions where we have the largest curvatures, which basically tell us the uncertainty space subspaces that are very well informed by observations, and then versus in some sense, even the Hessian, where the Hessian is almost rank efficient, so where there is almost the curvature is almost zeros, meaning these are directions in which they are poorly constrained. And we can now tie this together in this uncertainty chain, where you have here on the left-hand side, if you see my mouse here, so we come from a model data misfit, and this is an example for the North Atlantic, where we're trying to, we use, for example, the OSNAP array as an example, where we're trying to figure out sort of these OSNAP arrays. So we have a model data misfit. This informs the data here basically can inform the input, the uncertain input space, and say, okay, adding these data will reduce the uncertainty in our input spaces. So this is still, so this orange space here is a very high dimensional space, but we can then do a second step and actually say, how does this high dimensional uncertainty reduction then propagate onto quantities of interest that we're actually interested in? An example here could be Nordic Sea's heat content, or you can again think of certain transport metrics. And it turns out, if you go through the algebra, so we have a prior uncertainty that's given by basically the prior information that we have here, this V matrix, and then we have the sensitivity of our quantity of interest with respect to these uncertain input. And then here the posterior uncertainty is almost the same, the sensitivity of our quantities of interest, but now this is the posterior, and the posterior comes about by the data that have been assimilated into the assimilation system and hopefully have reduced the prior. Then we can ask for the uncertainty reduction, which is 1 minus the posterior minus the prior, and that gives us this equation here, which is a very simple equation. It's basically a scalar product, and the scalar product accounts for, actually let's go here, this is the scalar product sort of written out. This accounts for the sensitivity of the quantities of interest, essentially, on the one hand side, and then how it projects to the sensitivity of the misfit function. So these are the two important parts here. Sensitivity of the QI versus the sensitivity of the misfit function. And this is the projection on it. If they project poorly on each other, this means that the data sensitivity has poor information on the quantity of interest sensitivity. Another important sort of small detail here is this factor D in front of that projection operator. And D, if we write this out, which I haven't done here, but this gives us this can be interpreted as what we call the sensitivity to noise ratio. So what enters into this D is the observational error that we provide in the data assimilation scheme and the prior uncertainty. So you can think of if the prior uncertainty is very large, then we can potentially improve the uncertainty quite a lot. If this prior is very small, then we have to have very high, we have to have a really good sensitivity noise ratio in order to still make progress and get an uncertainty reduction. So we've coined this as dynamical versus effective proxy potential. So this one here, this scalar product here is the potentially achievable uncertainty reduction of the prior of the QI by the observation, and that is given. So the sensitivity to the observations of the observations projects very well sensitivity to the QI, and then but effectively that might be reduced by the sensitivity noise ratio, and we call this the effective proxy potential. I'm not going to go into it how to compute this. In practice, it's an eigen decomposition of the misfit Hessian. So you can think of it as Hessian singular vector decomposition on how you compute these modes. And some of it has actually just been published, and actually just last week in EOS has been highlighted, sort of a part one of hopefully a series of papers by Nora Lose et al. That basically is developing this UQ framework in the context of with its dynamical interpretation that underpins this. And so to conclude here, been asked again to give some recommendations, and some of them go back to actually recommendations that been placed in the Ocean Ops 09. And the very broad, I've given you a very specific algorithm approach. There are other people and other data assimilation scheme that will highlight different ways on doing this, and which is okay. The main point that I'd like to make is that really what is really needed overall is, especially in the ocean community, is to extend data assimilation to incorporate formal UQ to combine all of these sources of uncertainty. I think that numerical weather prediction is sort of ahead of the curve to what we've been doing in the ocean, and so we need to catch up. But of course, the reason why this hasn't happened is that the computational challenge is quite significant, and so it's important that dedicated effort should be spent to this, and also that a range of methods should be explored, right? So I'm highlighting one here, and there are others that that are available to us and should be explored. This requires sort of the collaboration between sort of us, the main scientists, and computational scientists. So this is an important part. That the quantitative observing system design is in some sense a powerful approach to assess uncertainty reduction. So framing observing system design in the UQ framework is actually a very powerful conceptual approach to that UQ can bring to the table overall as formulated and as observing system design. And ultimately, I'd like to say this is always an iterative approach, right? So we can, of course, always say, well, the models are not good enough to give us any of these information with sufficient accuracy. And I can only respond to that by saying, well, by going through this exercise, we learn also about the deficiencies of the model, like systematic biases and so on. And we learn through the algorithms of where they may be deficient, and therefore maybe how to fix them. So I'd like to conclude here with this, one line, sort of, it's a very broad, vision, sort of how you interact between observations, theory, and computational models, how, those interactions ultimately, hopefully bring us gain in knowledge. Thank you. I'm happy to take questions.
Thank you very much, Patrick. And thank you for the recommendations. I'll thank all the speakers. You've done an excellent job of supplying recommendations. The good thing of being the last speaker, Patrick, is we have this room till tomorrow morning, so we can spend all afternoon on discussions if you like.
Okay. Sounds good. I have to pick up the child eventually.
Okay. Do we have any questions?
So I have one. It's a slightly technical question, but let me ask anyways. So I was wondering, and I've been actually wondering this for some time now, that when you do this data assimilation for example, Argo data, do you assimilate the raw profiles or do you assimilate gridded fields?
That's actually a question. Yeah. So in very early renderings of Echo, so up to maybe 6 years ago or so, we have assimilated the gridded data. But since 6 years ago, well, what we call Echo version 4, we are assimilating individual profiles. So we assimilate profile by profile. And similar, the question might arise for satellite data, for example, altimetry, we assimilate a long track sea surface height data.
Cool. And can you say anything about the pros and cons of each approach? Is it universally better to work with the kind of the sort of the rawest type of data?
Well, I think the general, the mantra of data assimilation is that you should stay, your assimilation system should move as close as possible to the observation space, right? So, and anything starting from the raw, at least quality controlled observations, everything from then on would be part of what we call the observation to model operator. So this operator is also in some sense a model, right? So should be part of the assimilation algorithm. So as much as you can capture this operator within your assimilation scheme, the more the more faithful you will be to the entire method, and to incorporate this. And we think that the power of the adjoint method which gives you the ability to ingest the data at the position and at the time, right? That's the 4D VAR method, is in some sense that we are somewhat immune to these localization, issues, that if you see in other data assimilation systems, where you look at a product, you see a mooring being assimilated, and you see, very good, let's say, misfit very close to the mooring, but then that as you move away, things deteriorate, because what the adjoint does, it actually doesn't immediately correct the state at the point where you ingest the data. It just tells you there is a large misfit, and that misfit drives a linear model data sensitivity, and that sensitivity is propagated backward in time through the linearized model dynamic, and it's the model, the sort of the reversed linearized model dynamic that spreads out that information to where to the allowable controls, right? Yeah, not sure if it's become clear, but anyway, we are able to actually be close to the data without disturbing the dynamical consistency of the solution.
Cool, thank you very much. That's very helpful.
I have a question, a follow-up question. That means that when you're assimilating, let's say a fixed data point, that means that if you continuously assimilate that, your forecast, for example, becomes better, right?
Well, this is our hope. Of course, I did not talk about forecast here. So we are really, it's the echo in what I've talked about is strictly a reconstruction. But it
doesn't really matter. It just it could be a hindcast or a reanalysis. But yeah, once you continuously assimilate data, then the forwarding time estimate, whatever it is, becomes better, right? I guess that's my question.
I would definitely say yes. And there's some examples where that can be shown, where that has been shown. But yes, I would definitely say so. Yes.
Okay, and this assimilation could be at any scale. Can you assimilate a single point measurement, for example, or is there any issues with scaling?
Well, so yes and no, we do, right? So for example, we assimilate Argo profile data as pointwise data. But now what that means is that in the Echo version 4, which is nominally still a fairly coarse resolution model, especially in today's world, sort of nominally 1 degree, it's actually slightly better than that because of the way the grid is formulated. So we now have to actually worry in our uncertainty for the Argo data. We cannot just take the Argo, the nominal raw data uncertainty, but we have to think about the representation error. So what is the variability of a let's say 50 by 50 kilometer box in the at mid latitude over a 10-day period, or actually, sorry, this is more the 1 week because it's a pointwise, it's an instantaneous observation. But still, there is a variability that the model is not resolving, right? The mesoscale field is not resolved by the model. So we have to put this into as an added representation error. And there are papers written about, how to do the representation error, both in the atmosphere, it's the case, and the ocean is the case. And this in some sense is both a science problem and it's an iterative problem. Sometimes we're finding that we seek to find the best representation error that we have. But after the fact, we find that the residual misfit after going through an optimization exercise may point, so it should be white noise. You might argue that the residual would be just white noise distributed, but it's not, right? So it will be biased. There will be larger patches with a larger error here or of one sign, another sign. And this is what I've said, sort of this points us to something wrong somewhere in the system. And of course, it could be because of the model is just not able to fit the data there, or it could be that the uncertainties that we've provided, the representation error uncertainties are not have not been well estimated, right? So yeah, it's been pointed out. It's true that we yeah, sometimes. Oops, I'm sorry. What happened here? I was trying to click something else. Well, anyway, it's that these are all the uncertainty estimates that we have are actually estimates, right? So we are yeah.
Okay. Yeah. Thanks.
Yeah.
Patrick, I had a quick question. So like
Yeah.
one of the many applications of ECHO could be also to use the model to test some of the mapping methods that are applied to observations, like with the idea of like, if we had the information from the model at the same location as the observations, then we can use those synthetic profiles to map with different methods and compare to the model truth. And in that effort is very helpful to have an uncertainty quantification of that true field. But I was wondering, on a practical level, like, is that information available with ECHO? Like, is it easy for a user to access the synthetic profiles from the model? Is that information stored somewhere where people can access it and use it?
Yes.
Which I've done with other state estimates in the past. But ECHO is global, and it's it would be helpful.
So yes, it is, and I'm going to tell you in a minute why. But I also would like to caution. There's some but so yes, it is. If you go to the ECHO website, so echogroup.org, there you will we provide the full state, like any reanalysis product will provide you TS, the full state. We also provide these, what we call the model data misfit operators. So we have the model computes the model's profile of the Argo profile. And so it will actually generate, and it actually puts it out. And we provide all of these synthetic profile, exactly what you say. We actually provide them. They're available on the website as well. So you can work after the fact and offline. You can see how that one Argo profile, what the model profile looked like. So you don't actually have to recompute that. It's been because we had to write it out anyways, and so we're providing this on the ECHO group website. Now, of course, the issue there's two issues, right? So still, then becomes a question of what the truth is. So it's the model truth. And I'm not sure whether you were after just the model truth for this given, or whether you want to have sort of the best representation. This leads to the issue of nature runs in observing system simulation experiments, where in the atmosphere, people have been conducting very, very high resolution simulations that encapsulate most of the high frequency and high wave number variability in these nature runs to then do these OSSI type experiments. And that is of course not available because the model runs at the same resolution as we do the data assimilation. So if you were asking, do we have a much higher resolution nature run to underpin or to test mesoscale variability and high frequency variability of the system, we don't really have, we have that in a limited manner. Actually, so through what some of you may have heard of, these very high resolution ECHO simulations, these are available. But there again, I would caution is that it's a random mesoscale eddy field. And again, we have no ambition to at any time to fit exactly at every eddy in space and time, right? So this is something that is just not practical.
Thanks, Patrick, and thanks for a very nice presentation.
Are there any other questions? Then we'll end the session. I've posted the link to the Google Drive where the presentations are shown. The recording takes a few days to come up with it, but I'll post that somewhere as well so that you can replay if you're interested. And I'd have to replay yours, Patrick, about 100 times before I fully grasped it, I'll admit. But
the good thing is there's now a paper out, and there's also, I've put it in the last slides, I put in both a link to the paper, and there is a very nice story map, like ArcGIS story map, that basically tries to go through this idea of dynamical proxy potential. Yeah, might be helpful.
Well, I thank all the speakers and the participants. I'm very pleased with the turnout too. Thank you very much. And maybe we'll see you tomorrow morning. Well, for me, tomorrow at this next session. Could the co-chairs stay on for just a minute after this?
Sure.
If possible. Thank you.
Yes.
Okay, bye-bye. Thank you.
Bye-bye.
Thank you,
Thanks everyone for a great session.
Bye.
Bye.
Thank you, everyone.
See you tomorrow. Thank you.